Okay, all right. So I think we'll make it start on the second half. Um, and I was told that I have to stand up here because uh, apparently I'm being recorded. And so, so, so standing up here means two things. One is I can't really see my slides, but we'll try and figure out how to deal with that. And the second thing is I'm being recorded. I have to be more careful of what I'm going to say. You know, if you don't say too many rude things, but there'll still be some rude things. It'll be okay. Um, okay, so I looked at where I was during the break. We're actually basically at halfway through the talk, which is kind of amazing given um, how many interesting questions there were. And so so if you have more questions, we can accommodate them because we managed to get through half the talk in half the time. Okay, so I spent some time talking about mean field calculations, Hartree-Fock and DFT. Like I say, I'll use them synonymously. And what is the cost of a Hartree-Fock or DFT calculation? Well, in a standard implementation, the cost is typically about cubic with a system size, if n denotes the system size, or perhaps n denotes the number of particles, which is proportional to the system size. And this cost is spent building the matrix elements of the Hamiltonian and doing the diagonalization of this effective mean field Hamiltonian, the Fock operator, to get its eigenvalues and its eigenstates. And in a typical implementation, this cost allows you to treat between 100 to 1,000 light atoms. Of course, heavier atoms have more electrons and more expensive, and they're more expensive to compute. But light atoms means things that are in the first row of the periodic table. And such a Hartree-Fock DFT calculation on a single computational node, or perhaps a modern GPU card, may take minutes to hours. Right. So this is an example of a glycine peptide, 120 amino acids stuck together, 1,000 atoms, roughly speaking. And if you use a code, say this is a code from my group, you can run this on a single A100 GPU card in a few minutes, or a single node of the CPU, let's say that's 3 hours, something like that. Now, you can, of course, go beyond a single node and a single card, go to a supercomputer, and that buys you some more. So cubic scaling is not great scaling, but it's not terrible. I mean, maybe from this audience, cubic is essentially free, but of course, cubic is still something. So you can extend to 10,000 to 100,000 atoms, and the largest simulation that I'm aware of is a simulation done by Geoffrey Vidal's group when he was working at Google X, which was 30,000 atoms, done on most of a pod of a TPU cluster at Google, and they estimate if they use the entire pod, they could simulate close to 100,000 atoms. Okay. Now, when you want to go to very large systems, however, typically what people do is they introduce additional heuristics even at the mean field level to avoid this cubic scaling. And the way in which these sort of heuristics enter is you utilize the locality in chemistry. So typically chemistry is very local, atoms are very far away, don't really talk to each other, and this is sort of true at all levels of approximation, and so one can build that into the simulation itself. It's sort of instructive to see how these ideas enter at the mean field level. So as I'll say here, you can scale to actually much, much larger problems with only modest computation if you use these additional heuristics. And the basic idea is that the Hamiltonian is short-ranged. If you think of its matrix elements in a single particle basis, remember this is just a matrix of dimension of the single particle basis. By the single particle basis, typically the matrix elements decay exponentially when the atoms are separate, whereas the atoms, if you think about atoms far away, in a complexity perspective, you would say that this is a geometrically local Hamiltonian. And because this is just mean field theory, you can sort of make concrete statements about the ground state quite easily. And so you can say then that the correlation functions are short-ranged if the system is gapped. And in fact, that is known. You can prove this to be true so long as there's not a topological obstruction in the problem. So basically, this is true. And in this mean field sense, you're quite sure about this. And so because these correlation functions are very short, you don't have to compute all the matrix elements. And the correlation functions themselves are essentially just the Fermi-Dirac function that you compute from this matrix here. And if you imagine taking this Fermi-Dirac function and expanding it as some kind of matrix polynomial, the fact that you only want to compute out to some bandwidth of this matrix means that you only need to take the polynomial out to some finite order. And that finite order is independent of the system size because the range of these quantities is independent of the system size. So that's essentially what you do, and this allows you to make your algorithm go from cubic scaling down to less than cubic, and typically in gap systems, linear scaling. So that allows you to get to very large calculations. And you can do further things to make it cheaper, like you can simplify these matrix elements, and that way you can simulate up to 1 million atoms in this way. Okay. So, mean field calculations, density function theory, Hartree-Fock, as I'm sure you're aware if you've encountered chemistry in any setting, they're not exact. And very oftentimes you don't expect them even to be that great. But nonetheless, as it turns out, even in systems where we expect, say, density functional theory to be insufficient, as computational chemists, you actually spend most of your time still doing density functional calculations on the problem. So in a typical project, you may spend 80%, let's say 50% of your time first doing mean field calculations, and then 50% of your time, and they may be sufficient, in fact, right? But for problems where you know it's insufficient, then you might spend half your time just doing mean field calculation, and then half your time doing something else. So why do we do so many density functional calculations, even if we know that they're not necessarily giving you a faithful ground state, which is what you want? And so that's because, oftentimes, the question that you want to answer requires not just doing one electronic structure calculation, but first requires doing many, many electronic structure calculations. So an example of this is, first you need to obtain a good geometry. You need to know where the equilibrium positions of the nuclei are. So typically, you will carry out density functional calculations to compute, the potential energy surface and optimize the positions of the nuclei, and then just take that equilibrium geometry and then do a more sophisticated calculation. It's too expensive to repeat to many, many expensive electronic structure calculations. But there are other reasons why, and why you want to do mean field calculations. And one is that even if mean field calculation doesn't, reliably tell you what the ground state is, it might give you an idea of the low energy manifold of states. So in particular, if there are many different mean field solutions arising from nonlinearity, perhaps that tells you something about the excitation of the system, and that gives you some idea about the physics that's going on. And then finally, it's very common to start from a mean field calculation, which has already treated some of the electronic structure in some sense, to seed a more sophisticated many-body wave function calculation. And this last use, is really, I think of it as analogous to to doing state preparation. It's a sort of state preparation in the classical context where you're finding a good initial guess, and that really helps the more accurate method that you're going to apply later. So I'll just give a couple examples of how this classical type of state preparation appears. And so in the most common case, this sort of universally you do this. You first remember that in a mean field calculation, you're finding a good product state, and this product state involves optimizing your single particle representation, and it's in some ways giving you some optimal fermion basis. I mean, it's not quite optimal because it's just done at the mean field level, but it's typically much better than the computational basis that you started with. And so what you usually do after you've done a mean field calculation is you don't want to throw away all this information, and so you transform your Hamiltonian from the original computational basis into this optimal fermion basis. And then you start your many-body calculation. And then this, of course, removes a lot of the entanglement in the ground state, because a lot of it, in the original computational basis, there's all this entanglement. Mean field mixes up all those degrees of freedom, captures a lot of the entanglement, and you can get all of that for free, right? So you always, basically almost always do this in a many-body calculation. But there's sort of more subtle ways in which you use these mean field solutions for classical state preparation. And a typical example is encountered when you have chemistry where there are many different metals. The metals have, for example, different magnetic moments. Like I mentioned in nitrogenase, you have all these iron-sulfur clusters, and the ions have different magnetic moments. And those magnetic moments, can be arranged in many different ways. And if you run a mean field calculation on this system, you'll find that it'll produce many different mean field solutions corresponding to different orientations of the magnetic moments with different types of magnetic couplings, ferromagnetic, antiferromagnetic, and so on and so forth. Now, in this sort of case, density functional theory, whatever mean field theory you're using, doesn't really have the fidelity to distinguish between these different solutions and tell you what is the correct one, right? It just it might tell you this is the correct ground state, but it doesn't really have the accuracy for you to be certain about this. But what you do then in the many-body context is you just use all of these states as initial guesses to see these many-body calculations. And then your many-body calculation can sort of resolve and reorder the states so that you can confidently predict your ground state. So what happens is, let's say, use these to see the DMRG calculation or matrix product state calculation. It doesn't really matter what you use, but you use it to see some classical calculation with a tunable parameter where they get more accurate. And what happens is these original mean field energies will start to change, and the states will become reordered, and eventually you can get the correct state. Now, of course, you might ask, if you have a classical heuristic with a tunable parameter where, in principle, if you push it far enough, it gets you the exact answer, then why do you need to start from many different starting points? But the fact is that, although in principle, if I improve my classical heuristic and put more and more computational effort, every one of these starting points would go to the correct state. In practice, if you start from a very bad guess, it's very, very hard for your heuristic to recover without putting in an extremely large amount of computation. Right? So it's still nonetheless important to start from some reasonable initial guesses, and in practice, that's what we do. Okay. So it's just, we'll talk about quantum state peroration later in the talk, but it's sort of similar to that idea in the sense that, if you start closer to your solution, it really helps you out. And mean field can be used to provide many good candidate guesses for the structure of the ground state. Okay, so that's a good point to move beyond talking about mean field theory. And I'll just start by telling you a little bit about the physical intuition about what sort of effects happen outside of mean field theory. And then we'll go into the range of heuristics that we use to study electronic structure beyond mean field theory. Okay. So recall that the basic idea in a mean field calculation, a Hartree-Fock calculation, is that you first establish some effective solution of the one electron part of the Hamiltonian, which produces some one electron orbitals, and then you can build your many electron ground state just as a product state in this one electron and these optimized one electron orbital representation, and you just use a single product state. In chemistry, you might say use a single reference or single configuration. Okay. So as we now start to think about the many body effects, we now need to consider the difference between the Hamiltonian that gives rise to this product state, the mean field Hamiltonian, and the Hamiltonian that we actually want to treat, the Hamiltonian with the actual two particle interactions. So the state determinant or mean field state is an eigenstate of this type of operator. And we really want the eigenstate of the true Hamiltonian. So there's a difference between these operators, this perturbation or this fluctuation. And as I mentioned sort of earlier on towards the end of the last lecture, the effect of this fluctuation is to mix this valence configuration with other configurations of where the electrons are in other orbitals, not in the lowest state. And you think of two kinds of mixings. So one where this valence configuration is mixed where the electrons go to sort of faraway orbitals. This is a kind of a weak mixing because the orbitals are separated by a lot of energy. But it's nonetheless very important because there are many, many faraway orbitals. For example, there's a continuum of orbitals at high energies. And so there are these events where the electron is scattered from its mean field state into first weakly, but this scattering happens to many, many, many different orbitals. So quantitatively, this type of many body effect, which we call dynamic correlation, is always quantitatively important, even though conceptually it's kind of simple. It's just perturbative in nature. It requires, for example, large basis sets, so you can really treat these continuum contributions. Because this is conceptually simple, the effects of this weak correlation, although quantitatively are important, you can often capture them by rather simple empirical parameterizations. This is what density functional theory tries to do. It says, basically, I'm going to take the Hartree-Fock energy that's associated with this configuration, just add some empirical correction, and then turns out to not be too bad. But there are, of course, more principled ways that you can do this that can improve on the accuracy of DFT or give more reliable errors, and a lot of heuristics, many body heuristics try to do that. But there's, of course, the other type of correlation or effects beyond mean field theory, where the Coulomb matrix element scatters valence electrons in between the different valence orbitals. And in this case, the energy separation is comparable to the Coulomb matrix element, and you can mix basically very strongly with other configurations. Right? So in particular, in systems where this splitting of the valence orbitals is basically comparable to the size of the Coulomb matrix elements, then you expect to mix lots and lots of configurations. And this is what we call a strong correlation or multi-reference electronic structure. So these things, doesn't always happen, right? So I mean, you can have systems where the splitting of valence orbitals is very large, but the Coulomb matrix, let's say 1 eV, but the Coulomb matrix elements are relatively small, let's say 0.2 eV, then these kind of effects don't occur. And so you can ask, where does this typically occur, right? So you don't always have strong correlation, but there are certain problems where this happens. And in chemistry, it sort of happens at certain geometries of molecules. In particular, as you change the bond length of a system, you change the splitting of the valence orbitals, and you can reach a region where the valence splitting is comparable to the Coulomb matrix element. And this is why typically at intermediate bond lengths, where the valence splitting is not much larger or much smaller than the Coulomb matrix element, the uncertainty in quantum chemical predictions is typically largest. And it can also happen by choosing certain elements in the periodic table, right? So this is the periodic table. There are these blue elements and these green elements. The blue elements are the transition metals. The green elements are the lanthanides and the actinides. And in these elements, you have atomic orbitals that somehow don't extend too much out of the atom. They're called D shell or F shell orbitals. And so they only have relatively weak splittings when you try and combine other atoms with these elements. And this relatively weak splitting is often comparable to the Coulomb interaction, or even, and so you have strong correlation effects. Okay, the classic condensed matter way of viewing this, is also useful. And in the condensed matter viewpoint, it's best described in terms of models. So we'll talk about the Hubbard model. And so all the terminology I was using just before can be understood in the Hubbard model by understanding that each site in the Hubbard model is just the atoms, right? So each is one atom. And then the T term in the Hubbard model is the bonding, right? This is related to the splitting of the valence orbitals. And U is the Coulomb matrix element. And basically in the Hubbard model, the bandwidth for the total splitting associated with the electrons just hopping around the entire lattice is proportional to T. It's 2 times the hypercubic lattice, 2 times the spatial dimension times T. And we define the strongly correlated regime of the Hubbard model as being when U is greater than 2 times dt. And this is what you encounter, for example, in the cuprate-like parameters for the Hubbard model. Now, I've been emphasizing the case where the Coulomb matrix element and the hopping matrix element become comparable in magnitude as giving rise to a lot of complexity. Now, there's, of course, an additional limit where the Coulomb matrix element becomes much larger than the single electron matrix elements. Now, in that limit, the physics it simplifies in some ways, but can still be complicated. So as U goes to infinity in the Hubbard model, then the particles can never occupy the same site, right? Because to occupy the same site, this U, which is the energy penalty for 2 particles being on the same site, is infinity, right? So these doubly occupied states are projected out of the problem. And you can imagine a system where the number of particles, let's say, you set it to be equal to the number of sites. And then in this case, because U has gone to infinity, every site can only be occupied by a single particle. So there's some sort of reduction of the Hilbert space. But there's still a degeneracy because the particles are spin half particles and they have this 2-fold degeneracy or spin on each side. And so in this limit, of course, there's a new emergent energy scale, which is the exchange energy, and the Hubbard model reduces to essentially the Heisenberg model. the Heisenberg model can involve strong correlation and it cannot. And it's a more complicated procedure to decide whether it does or not. Essentially depends on whether the model has frustration. And when it's frustrated, then you again get this situation where you need to mix together many, many different types of configurations. Okay, so with that sort of general statement about types of correlation and how we think about them, the intuition about them, let's now just think about them. I'll just give a list of classical heuristics that you use to go beyond the mean field treatment of electronic structure. And there's a lot of them. I mean, you know, quantum chemists have been writing papers for a long time, so they produce lots of methods. I mean, lots of methods are not good methods, but nonetheless, people still produce lots of methods. And so I can't tell you about all of them. I'll just cover some of the groups. And you know, one way to think about, I basically got to talk about, I think, 6 different ones. And for applications to chemical matter, you can think about, you know, heuristics along the following axes, right? Is it something you use when the problem, where the main challenge is describing the dynamic correlation? In other words, that's the sort of weak scattering, but to a very large number of states. Or the strong correlation, that's a sort of non-perturbative rearrangement of the valence electrons. Or perhaps you can, the heuristic describes both. You know, is it systematically improvable? In fact, everything I would describe here is a heuristic that can be improved. In other words, there's a parameter you can tune to make it exact. But there are some heuristics which are not. Is the energy extensive? This means that if I were to treat a collection of identical systems, does the energy scale linearly if I take a collection of non-interacting, you know, if I take a collection of non-interacting atoms, right? So, without requiring an exponential cost in the calculation. So this is a prerequisite for treating very large problems because, I mean, extensivity of the energy is a basic sort of physical phenomenon in the thermodynamics when you get to larger systems. And then closely related to that is how does the cost scale as a function of system size? What are the prefactors? And can it be used with very complicated Hamiltonians, or does it require the interactions to be very simple? Okay, so like I said, I'll just go quite quickly, I think, now through this laundry list. And we can discuss the details if you have questions. So the simplest idea is just something that you call configuration interaction in quantum chemistry. And the idea here is that, you know, Hartree-Fock treats one configuration, so you just linearly mix with other possible configurations, and you just variationally determine these mixing coefficients. So you just diagonalize the Hamiltonian in this space of different configurations. If you include all possible configurations, then of course the method is exact, and you call that full configuration interaction or exact diagonalization. Now, you know, the idea is very simple, right? You can treat any kind of correlation this way if you include enough configurations. It's clearly improvable. One challenge with this approach, however, is that unless you include an exponential number of configurations, right, like as the system size grows, because the Hilbert space is growing, right, exponentially, the method is not extensive. Okay, so if you choose a truncation without an exponential truncation to anything less than an exponential number of states, your energy gets worse and worse as the system size grows. So the cost of this method, well, you know, if you use any truncation, you usually truncate to a polynomial number of terms. You know, the cost is usually polynomial, but you know, this is not very meaningful because in large systems, the energy would scale in the incorrect way. Nonetheless, it's a very simple method. Prefactors are low, and you can use this with many different kinds of Hamiltonians. Today, configuration interaction is not used a lot in chemistry, except in one context when where it's used to treat the strong correlation problem amongst a small number of valence orbitals. So you have electrons in some bonding event where there's a lot of rearrangement of electrons between a few orbitals, and then you say, let's just diagonalize the problem. Okay, that's just doing configuration interaction. Okay, another very simple idea, right, is to use perturbation theory, right? And here, one understands that the starting point is a very simple state, a Slater determinant, or Gaussian state. And in perturbation theory, the idea is that you connect this initial state to the interacting state either by real-time evolution or by an imaginary time evolution process. Here I've written down the imaginary time evolution. And in the interaction picture, the imaginary time, because this initial state is an eigenstate of a simple operator, then the imaginary time evolution can be written in terms of just this perturbation in the interaction picture. And so here I have the state that's been evolved to the ground state, and then I just expand the exponential in the Taylor series. And so the Taylor series is the perturbation theory. This is sort of the foundation of many body physics going back to, I guess, the 1950s now, right? So, and the idea is that, I've written this funny term here, connected. And the idea is that, if you now look at this in more detail and understand that these are operators involving, let's say fermionic particles, you have expressions with fermionic operators, and you can apply Wick's theorem to evaluate everything. And then you can identify that certain contributions to these terms correspond to ways of choosing correlation functions in Wick's theorem that look like they're connecting different operators. Without going into the details, as I can't teach you all about many-body perturbation theory in one slide, but you can draw a picture to illustrate the different contributions to Wick's theorem, and some of them look like they're all stuck together, and we call those connected diagrams, and some are disconnected. So this is sort of the Feynman diagram expansion. And the key idea in many-body perturbation theory is that this expression involves the sum only of the connected diagrams. Okay, but in any case, you can identify diagrams you want to conclude. You can do perturbation theory to fix orders. You can resum certain families of diagrams by some geometric series or by some iteration, and so on and so forth. So there's a very, very rich structure of many-body perturbation theory as befits something that has been sort of a cornerstone of physics for 70 years. So it's applied in many ways. It's not usually a convergence theory because the perturbation is very strong. The difference between the mean field Hamiltonian and the true Hamiltonian is not a small term. But at finite order, it can give reasonable results, and resumming certain things to infinite order can also work. And so it's very closely tied to the starting point. So often it's really only used to treat sort of dynamic correlation. It's improvable. It's extensive at any finite order. It scales polynomials. It's very, very cheap. Okay. Yes, go on. Yes. Yes. Okay. So in this context, it means if I do perturbation theory to a fixed order, like second order, the energy is extensive, or fourth order is extensive.
I see.
Yeah. A truncated version. Yeah.
I think you didn't. So
actually, this is not a free energy. I mean, it looks the e to minus beta. It looks like there's a free energy, but here this is actually just the imaginary time propagation of a state to the ground state.
So the F is not the free energy.
No. Also, sorry. So F here is the Fock Hamiltonian, of which your initial Slater term is an eigenstate. Okay. Yeah.
Could you clarify what you mean by it doesn't convert? What is it?
Well, if things don't converge, it means if you add more terms, they don't go to.
What I meant is that, is it because it's on this side, other side? No, I'm on the other side.
Okay, well.
Anyways, yeah.
Okay, all right, yeah.
So, what I meant is that the infinite order Dyson series converges to the true value. So you're saying at a truncated, if you truncate it at a certain number of terms, it doesn't converge.
No. So it doesn't always converge. Yeah, the infinite order series doesn't always converge. So in particular, I mean, you can write it down, but you just find that. So one way in which it doesn't converge, for example, is that might sound not so strange, right? Is if you start with a ground state that's in the wrong phase, you will find that but you start with the Hamiltonian where a ground state of another phase is the correct ground state. You will find that you can never find the correct energy. But more trivially, the reason it doesn't converge in molecular systems, so for the following reason. So the Taylor series expansion. You have to consider the radius of convergence requires you to consider the perturbation in the complex plane. So in other words, if I apply the perturbation, you have to think about what it's doing not only at the value of the perturbation, but minus the value of the perturbation, or any complex number times the value of the perturbation. You have to think about the Taylor series of the complex plane. And if you go from sort of the positive value of the perturbation to the negative value of the perturbation, that can actually become some kind of attractive interactive fluctuation. And you often get a phase transition. There's often a pole in the complex plane that corresponds to some phase transition, because you have matter and an attractive interaction. It often produces a very different ground state than the mean field ground state you started with from a repulsive interaction. So that's the sort of technical origin of the divergence. Okay. And so then another heuristic is just a laundry list in some sense. That's what sort of, computation. There was that statement about all science outside of physics is stamp collecting or something like that. So anyway, this is a little bit like that. Okay. So coupled cluster theory is a type of ansatz. And so if we recall that the Hartree-Fock state, can be written in this form. So the Hartree-Fock Slater determinant can be written as some exponential of a quadratic form acting on any other product state. The coupled cluster state is really just a generalization of this. So you can imagine that instead of this exponential stopping at the quadratic term, you can add the quartic term and the sextic term and the octic term and so on and so forth. And that's basically the coupled cluster ansatz. Now, you give these things names, right? So the quadratic term you call the singles, the quartic term you call the doubles, and next term is the triples. No prizes for guessing that. And so you have a series of acronyms, CCS, CCSD, CCSDT. In practice, when you apply coupled cluster theory, you make some additional restrictions, so you don't use this most general form, to enable you to calculate matrix elements easily. And so for example, the classical application of coupled cluster theory in classical computers, if you look at the singles term here, you usually restrict it to be a destruction operator that destroys only orbitals that are occupied in your initial state, and then a creation operator that only creates orbitals that are unoccupied. And this, with some additional considerations, allows you to evaluate some kind of expectation value of this in a reasonable way. But on quantum computers, of course, what you'd really like is for this exponential operator to be a unitary operator. And so when people talk about coupled cluster on quantum computers, they usually use a unitary variant, where in the singles case, you choose I times a Hermitian object. So this entire thing is just unitary, and so you can implement it with a circuit. Okay, so coupled cluster theory is the most popular quantum chemistry method after DFT, right? So for every 1,000 people who do DFT, the one person is doing coupled cluster. And the reason why is that at least at the weakly correlated level, coupled cluster up to a reasonable number of excitations is extremely accurate. It will always yield chemical accuracy. And it can also treat moderately strong correlations. So it extends not just from the weakly correlated things, but it can also give reasonable descriptions of bonds breaking and things like that if applied in the right way. So it has many nice characteristics, weak up to moderately strong, it's improvable, and so on and so forth. It has a polynomial cost, an OK prefactor, and can be applied very widely. Okay, and then finally, two other general heuristics. Okay, so the first is going to be DMRG. Okay, so DMRG, or matrix product state, is probably more familiar to this community, is a variational ansatz where you restrict the structure and amount of bipartite entanglement in the ansatz so that classical computation is efficient. The matrix product state name arises because if you think about the amplitude for a given computational basis configuration, so a given value of n1, n2, n3, n4, so I fix these superscripts here, then the value amplitude is given by the product of a vector times a matrix times a matrix times a vector. So it's just a matrix product. There's some nice notations associated with illustrating its structure. And the ansatz is systematically tunable because you have these matrices, they have some dimension. If you make the dimension larger, you can capture more entanglement. and so the ansatz becomes exact. It's a provably efficient ansatz for 1D lattice ground state problems in the sense that if you have a one-dimensional local Hamiltonian with a gap ground state, then you know that its ground state can be expressed efficiently by a matrix product state. And then with some additional caveats, you can even find the ground state efficiently. And so it's a standard tool in condensed matter applications in 1D, and even in two-dimensional applications, it's used to simulate two-dimensional lattices up to a finite width. Now, of course, chemistry is not really about one-dimensional problems, at least most of the time. And so people are sometimes surprised why DMRG has a role to play in chemistry. But the fact is that, for difficult problems, there are not so many tools to use. And DMRG always allows you to go beyond exact diagonalization, right? So exact diagonalization is this extremely expensive thing that you can only do in a very large system, and DMRG can always treat a larger system than exact diagonalization. So it's kind of this niche tool that you bring out for hard problems where all the other methods fail to yield a qualitatively correct solution. And that's how it's used. So, it has various properties, some of which are nice. In practice, though you can, of course, treat any type of correlation this way, if there are better methods to use when the correlations are not very strong. I mean, it's a very expensive method in general. It has very large prefactors. And so if you have a weakly correlated molecule, you should just do coupled cluster theory or DFT. Okay? But for very hard problems, it's a good thing to use. Now, of course, DMRG is a very old idea now. We just had an article about it 30 years, DMRG 30 years on, where we gave some reflections on, Steve's seminal paper in 1992. And since then, more general types of variational ansatz have been proposed, and we now know that matrix product states are just, a example of more general class of wave functions known as tensor networks. And tensor networks, I extend this idea of providing a low entanglement ansatz in a natural way to two-dimensional and three-dimensional problems. And so the basic idea there is that the amplitude of the wave function is obtained not by contracting a product of matrices, but by contracting a product of tensors. And so another name that is sometimes given to tensor networks is that they're tensor product states. Although that is liable to some confusion because you might think it's just a product state, right? But it's a product of tensors. So it's nowadays a very powerful technique in lattice models. The cost is linear in the size of the model if the tensor network has sort of the right structure to match the entanglement. And an example of a kind of modern calculation of this is one of the calculations from our group is that if you take the two-dimensional Hubbard model on sort of on a lattice with a reasonable width, you can spend your time doing DMRG calculations up to really, really large ones, and the energy is converging very slowly. But you can do PEPS calculations, and as you increase the bond dimension of the tensor network, this is one of the bond dimension, you see that these two-dimensional tensor network calculations really are useful tools. They really allow you to go beyond DMRG in lattice models. And so, yes, go on.
What kind of systems something like PEPS can't treat very well? What are the...
So I would say that this is one limitation, however. So although these tensor networks have all these very nice formal properties, in practice, most of the algorithms they're associated with assume a very simple structure to the Hamiltonian. So they work very well with model Hamiltonians. And extending these techniques to more realistic interactions is just an open problem. So people haven't really done that. Or they haven't done it successfully yet. Yeah. Okay, and then the last thing I'll talk about are quantum Monte Carlo methods. This is a topic an entire topic. I mean, everything I've said every slide is really an entire topic, but quantum Monte Carlo is very hard to describe succinctly because there's so many different quantum Monte Carlo methods. But roughly speaking, there are two families. The first is variational Monte Carlo, which is very simple, easy to understand. And the idea there is if you just take the energy expectation value, you can insert some type of basis, perhaps a computational basis, and rewrite it in this form. So I inserted a resolution of the identity, and then
I multiplied by the wave function amplitude and divided by the wave function amplitude. Otherwise, so these two things are identical. But writing in this way, you have the wave function amplitude squared, and this is a probability distribution. It's a Born distribution, right? And so I can think of this as a probability distribution which I sample from. And you can sample from it using the Metropolis algorithm, for example. So you don't have to sample directly. You can just sample by a Markov chain. So then you sample these configurations, and then you can compute this other quantity here, which is called the local energy. And then that's the variation Monte Carlo procedure. So it's very simple, and it has many nice properties. So one thing is that you can write down any form as long as you can just evaluate the amplitude, and then you can use it in variational Monte Carlo. So it allows very, very general mathematical forms to be used. And in recent years, because again, of neural networks, there are all these new ways to parameterize functions. Any of those things you can use to you can use in the variational Monte Carlo context. The second thing is that you can, when you insert this basis in which you're sampling from, it can really be any basis, and it can even be a basis in a continuous space. So you don't need to. So this is the sense in which quantum Monte Carlo doesn't require you to discretize your problem. It's just like in the way that you can evaluate an integral by Monte Carlo just by sampling different real space coordinates. You can evaluate this integral associated with this expectation value by sampling different real space coordinates. But it has a number of disadvantages. I mean, one is it's stochastic, so you need to take a lot of samples. You have to beat down that stochastic error. And it's a variational problem, so you have to optimize your parameters in the presence of all the stochastic noise. And this is a real pain. And this is, I think, the main issue with the problem, with approach. The second common type of Monte Carlo is projector Monte Carlo. And there are many things that fall in this category. And the basic idea here is that you're really sampling an imaginary time path integral in a sense. So what you're doing here is you're saying, let's take the wave function as the limit of imaginary time projection on an initial state. So if you do eta minus beta h and take the limit of large beta, this will project any initial state to the ground state. And you think of this projection process as occurring in many tiny steps. So you project for many short times. And so it's a product of many short time projectors. OK, so each projector is an operator, so it's a matrix. And so if we want to sample this process, it's the same thing as sampling a chain of matrix multiplications. So each projector is some small matrix. I can evaluate the matrix elements, and then I just sample all the terms involved in this matrix multiplication. So that's the basic idea. So you do the sampling. If you sample enough, you'll have sampled the representation of the ground state. It's very, very closely related to path integral sampling. So you imagine sampling a particular choice of coordinates, a choice of indices in this matrix multiplication. It defines a path, so to speak. The only problem with this approach is that if you imagine you're multiplying all these objects together, you can get very large numbers. And in particular, the matrix has both positive and negative entries. You can obtain very large positive numbers and very large negative numbers. And so when you add up all the contributions of these paths, some have very large positive weights, very large positive numbers, perhaps exponentially large positive numbers, and then they're very large negative numbers. And then your signal is the difference between these two exponentially large quantities. And so this is the Fermi-Einstein problem, and it's a basic problem with this approach. But you can control the sign problem in various ways. For example, you could just throw away all the negative contributions. And that sounds like a bad idea, but that's in fact something that you can do. Usually you throw away the negative contributions after doing some type of important sampling, and I can't get into all the technical details, but that's what people essentially do in practice. So they throw away the negative contributions after some type of reweighting of the problem. OK, that gives rise to all these particular names here, like fixed node, phaseless, and so on and so forth. These are all different ways of throwing away the negative contributions. OK, so Monte Carlo methods are nice in many, many ways. They're extensive, systematically improvable, and so on and so forth. Prefactors are large. For variational Monte Carlo, they're large. For projector Monte Carlo, they're really large. OK, they're very, very large, enormous. But they have many nice properties, and this is why people are interested in them for various applications. Okay, all right, so that's a long list. And it's just a short list compared to the actual list of methods there are, but gives you a flavor of things that that people can do. Now, I've mentioned that all the heuristics that we use, we use them in some way so that they have a polynomial scaling with system size. But as I mentioned, polynomials doesn't mean practical, right? And so, cubic is sort of okay, but if you think about coupled cluster, even at the level you typically truncate it to, it has sort of an n to the 6 or n to 7 scaling with system size, and that can be quite painful, right? So the border that we consider, I would say, in the field as being practically useful is, n cubed is pretty good. N to the 6 is getting to the scale where it's becoming, it's only sometimes useful, and anything worse is just, is impossible. So that's a more fine-grained view of polynomial complexity. To just give you an idea, right? I mean, this is just simple arithmetic, but you might want to ask, like, how much time does it cost? How long should I wait if I want to just increase the simulation size by a factor of 10, which is not a lot. If you're simulating the thermodynamic limit of the material, it's reasonable to see if things change when going from 100 to 1,000 atoms, for example. And if you have n to the 6 scaling, that's 1,000,000 times in cost. And then you go, oh, but computers, are getting faster, or if at least they're not getting faster, I'm getting more of them as time goes on. And so you can take Moore's law, which is a doubling of computing capacity every 2 years, as it's stated these days. But to get to 10 to the 6, that's 40 years, and that's one academic career, right? One academic lifetime, and that's longer than you typically want to wait. So that gives you some idea of the, how we think about these scales. But just as you could introduce locality to reduce the scaling, as I sort of discussed in detail in the mean field case, you can modify your heuristics to enforce locality. And this is what people do in practice to simulate large systems. And you can even get down to order n or linear scaling algorithms. So in the coupled cluster context, the way this would work is you have, for example, this complicated operator up here, where all these are creating or destroying electrons on different atoms. But you might say, let's say, set all the coefficients here to 0 if you're trying to create things that are on very widely separated atoms. Presumably, that process is not very important. And you can treat this cutoff for the distance over which you allow things to be created as some convergence parameter and monitor that in your calculations. OK, so let me just complete this part with did you have a question? Yes.
Can you explain why CCSD was
n to the 6?
Yeah, n to the 6, and
Oh.
CCSDT was n to the 8.
Yeah, I mean, it comes from the equations from evaluating matrix elements, and yeah, I mean, there's the multiplication of 2 quantities, each of which has 4 legs, and you contract 2 of them. So you just look at this tensor contraction as n to the 6. I mean, I don't think there's a.
So what would the quadruplet be?
So you mean why is the triples more expensive?
So how does it? I mean, like CCSDT.
Q?
Q.
Oh, that'd be n to the 10. Yeah.
Okay,
Yeah.
so it goes up by.
Yeah. It goes up by 2. Yeah.
Is there any hope of or way of doing better than order n?
I think that like just from the presence of just from information theoretic perspectives, you cannot do better than order n if you want to really know uniformly about all the parts of your system, because there's order n in a piece of information. So the only way in which you can do better than order n is if you're thinking about a system that somehow it doesn't have that much information. So if it is just uniform, right? And let's say you want to look at a local observable, then you imagine that you don't need everything around. You should have, in fact, order 1 cost to compute the local observable, and so in those cases you can do better than order n. So okay, so I don't know if we should go into the story. Maybe I'll just skip it. But just very, very quickly, I just wanted to say that sometimes to solve difficult problems, the short story here is that you need to apply multiple kinds of heuristics. I've listed this long laundry list, but in practice, you often use many of them in conjunction to solve a problem. And the problem that I was going to tell you about was this chromium dimer molecule, because it's sometimes discussed as a molecule whose simulation requires a quantum computer to get the right answer. But as it turns out, it's something that you can actually do quite well by combining heuristics in the classical setting. Okay, all right. If you want to know more of that story, I'll tell you after the talk. Okay, so to summarize, mean field theories are theories which provide most of the intuition behind chemical understanding, and very often, really more often than not, it's surprisingly so the case, electronic structure is qualitatively very close to one of your mean field solutions. It may not be the mean field solution that the mean field is telling you is the lowest energy solution. It may be another energy solution, but in my experience over 30 years of doing this, that we always want to see something very exotic. It kind of excites you as a theorist, but almost all the time the answer is the least exotic answer in physical problems. There are many heuristics beyond mean field, and there are some qualitative gaps in capabilities, typically associated with more strongly correlated problems and treating them with very large basis sets, for example, or treating strong correlation with more realistic interactions. So there was a question about, tensor networks and what can't they do? Well, nowadays you can use tensor networks with model Hamiltonians, but it's just very difficult to use them with, realistic Hamiltonians. And then through incorporating locality, you can scale many of these heuristics up to large systems. And the last story was meant to show that although there isn't really a theory of error, you're just applying these things, hoping that you're getting a reasonable answer. Sometimes you have no estimate of error. This may sound like a complete disaster, but in practice, it is remarkably successful, and it's the basis of the discipline of computational chemistry. Okay, so I now want to move on to the last two topics in the lecture. Okay. Oh, okay, you can go ahead, yeah.
Oh, okay. We know from like the Kohn-Sham theorem that like every chemical system admits like a mean field picture, basically, right?
Yeah. If you fix up its energy, right? Yes.
Yeah.
Because the Kohn-Sham, it's only giving you the only observables you're getting directly out are the energy and the density. Yeah.
Okay, fair enough. I guess can you but in terms of choosing the heuristic, there's a kind of post hoc protocol in some sense, right? Like it's not ab initio. You sort of have to make a guess and then see if it works and then refine your guess again. Can you comment about like sort of the hidden work that needs to go on in sort of refining those post hoc protocols? Like there's a sense in which like, oh, you sort of come at it from the end where you say, oh, DFT worked, but actually it took like a long time to get the right effective potential or something like this.
Yeah. So there are different things. So there are basic heuristics for which you have no internal measure of whether the method is working or not. So density functional theory is one such theory. And so the only thing you can rely on is the general experience of density functional theory applied to other problems and some empirical understanding of when it works and when it doesn't work. So in those cases, you apply it, and based on other examples, you have some feeling that it's working, but you're never really sure.
Yeah.
Right. And then in all the other heuristics I showed, there's always some internal convergence parameter. And so if you look at it and you just look very far from convergence, you just feel very uncertain, and then you say, well, and then you try and look at what is making it not work, right? And often there's some other structure in the electronic structure, like, well, really these two orbitals are very strongly correlated. I'm seeing this perturbation becoming very large or something, right? And then you have to, put on another, try something else.
I see.
Right, and then the unsolved problems are one where none of this works, right? So you're not able to converge anything satisfactorily.
Just as a follow-up question, sorry, thanks for taking the time. In the context where the convergence parameter does tell you that it's working, how confident are you that that convergence factor is giving you the right signal, in the sense that like it could converge but still give you the wrong answer?
Yeah. So this was a how confident is a kind of psychological question, I think. But I think there is no guarantee, right? Okay. But what you do in practice is you either refer to other examples, Or something that's becoming more common is you take two different procedures which have very different assumptions and have their own internal convergence parameters,
I see.
and then you try and converge both of them, right? And you're a consistent answer, then you feel
Thanks.
more confident. Okay, so last two parts of today's lecture are somewhat shorter, but they're concerned maybe a little bit more with complexity questions rather than all the sort of chemistry and heuristics questions. Okay, so the first is about the complexity of classical simulation and sort of understanding when is it easy or hard for chemistry. Should you think of it easy or hard? When is it easy or hard to do classical simulations? Okay. All right, and so, what do we know about the complexity of classical heuristics? Well, what we do know is the runtime cost, right? Because you apply a classical heuristic and you apply it so that it's a polynomial cost algorithm, otherwise you wouldn't use it. But you don't know the error associated with your algorithm. And so for proper characterization of the complexity, you of course want to talk about the cost to achieve a certain error. And as it turns out, there will be no theory of error because these are some heuristic algorithms are very difficult to analyze. But you can get some understanding of the error just through a lot of empirical observations. Nonetheless, obtaining this full characterization of the complexity of heuristics is very seldom done. And I think of it as an important open question. I mean, in the field of quantum chemistry, thinking about complexity in this more rigorous way, rather than just the runtime to be able to run the algorithm, but think about the runtime to get an error, it's just something that people haven't done very much because you're focused on solving a problem. So first you have to get your algorithm to run, and then you're like, oh yeah, did I get the answer? Do I get something useful? But as quantum chemistry has intersected more with quantum computer science, particularly through the field of quantum information, the attention is now sort of turning towards the more rigorous characterization of complexity. So before I talk about what I know about what I think is the way you should think about the complexity and the error, let me just talk about what error means in chemical systems. This thing is related to a figure that will appear in a minute, not the title. So usually you say in chemical problems that you want to reach chemical accuracy in the energy, and this number is 1 kcal per mole. Someone asked me, why is it 1 kcal per mole? This is kT. So if you turn just the typical thermal energy, fluctuation energy at room temperature, it's about 1 kilocalorie per molecule. But what does this, when I say what does this mean, the question is, what quantity is this an error in? If you take a large system, right, in particular, if you take the thermodynamic limit, right, its energy will just diverge. Its energy will become infinity. And so it's not actually very meaningful to think about computing the energy in the thermodynamic limit, for example, in a very large system, to the chemical accuracy. So when people actually introduced the term chemical accuracy it was introduced by Popel in the 90s, it wasn't a measure of the error of the absolute energy. That's not really what the meaning is, although this has become the meaning today because in the quantum information and quantum computing kind of literature of this is what is always stated as the error in the total energy. But in many or most applications of chemistry, what we're actually interested in is some kind of relative precision or relative error, namely the error per atom in the system. And it's really that which you really want to compute to chemical accuracy. So to drive this point home in a number of other ways, so if you just think about the statistical mechanics or statistical description of matter, we always say that different ensembles yield the same predictions for the bulk phases of matter. But the different ensembles only yield the same predictions for, let's say the energy divided by the number of atoms, not for the absolute energy, right? And so, to do statistical mechanics properly, we want E over N to be described correctly. And that's the way in which you distinguish between different phases, for example, right? And similarly, if you have a chemical reaction, chemistry involves only local changes. So an extreme example of this is click chemistry, and this is where this Nobel Prize reference comes from, because the Nobel Prize was awarded for click chemistry in 2021. But this is a particularly local type of chemistry, where if you take any molecule, you can have almost anything on it, and you attach this particular functional group, set of atoms to it, and this other molecule has this thing attached to it, then regardless of almost anything around it, then these two things just stick together. They click together, and the remaining sort of molecules in the end are left almost completely unchanged, essentially unchanged. And so if one's interested in the energy of this click reaction, you're looking at the energy of this state minus the energy of this state, but the molecules are unchanged. So the molecular, these sort of giant circles, which contain a lot of energy, those energies cancel. And what you're interested in is just this energy of this event, which is really an energy that's just distributed over a couple of atoms. Right? So that's the sense in which one wants to achieve chemical accuracy to impact the description of chemistry. Okay. So should we think about targeting just a relative precision? And is that what heuristics should do? So actually, most classical heuristics, in fact, do target only the relative precision. And they can successfully do so because the energy error that they induce is, in fact, sort of very local. And what I mean by this is, let's just think about the problem of introducing a basis, so discretize the problem. Okay, this is, again, some kind of heuristic, okay, depending on how you do it. And this introduces an error, and the error, of course, grows with the size of the system. But if you consider chemical reaction, the error that you make in the sort of discretization of this molecule cancels in this energy difference. And so when you think about discretizing the problem and you treat larger and larger systems, you never in a natural simulation think, oh, I must increase my discretization to be finer and finer because my molecule is bigger. That sounds very strange. You use the same discretization even as the molecule is getting bigger because the energies cancel when you subtract two energies. So many heuristic ansatz have this error property. They kind of make a local error in the energy. If you consider mean field, for example, it kind of messes up the description of every atom a little bit, right? And as long as the atoms are not changing in the chemical reaction, that error cancels between two different energies. And so you can think about relative error as the right metric. But there are some exceptions. For example, stochastic error doesn't behave in this way. And if you are trying to converge a stochastic error, it's just this random error. It's not that sort of correlated to any local feature of the problem. Then you really need to converge a stochastic error to this absolute precision. Okay, so having that aside about error, I want to then introduce this idea that when you're thinking about the errors in classical heuristics, there are really two kinds of errors. There's one which I will call the reference error, and you can think of this as related to state preparation. And then the second error is a refinement error. And to illustrate these two different kinds of error, let's look at a heuristic simulation of the potential energy surface of a diatomic using coupled cluster theory. And coupled cluster theory, as you recall, needs some starting point, some particular mean field starting point, and then you solve for this exponential operator, which improves the starting point or refines it to give you the correct wave function. So here are some potential energy curves, and they're obviously drawn by hand, so they're not meant to be truly quantitative. But this black curve here would be, say, the exact result. We saw this type of curve earlier, right? And then if you do the mean field calculation, you obtain a solution which looks like this red curve, right? Which doesn't look very good and isn't even quantitatively quite right because, for the molecule to dissociate, this energy should go to 0, but it doesn't go to 0 here. But if you now apply coupled cluster theory onto this mean field solution, you will attain something like, even at this low level of truncation of this operator, you obtain something that looks like this green curve. And you see this refinement of the energy is extremely good. So it's very, very close to the exact result, up to some point where it starts to go wrong. And then, as it turns out, close to this point, however, if you look at your Hartree-Fock equations, you'll find that there's another solution of the Hartree-Fock equation. So the nonlinearity gives you another solution. And that solution is this purple curve here. And so then, if I start from this other starting point, or this other reference, and I do coupled cluster theory, I obtain this yellow line, which is now much more reasonable. Okay, so the refinement error refers to the difference between the black and the green curves in this region, right? And the reference error, which is a kind of state preparation, refers to picking the wrong Hartree-Fock state in this stretch region. And I think it's useful to think about these two errors as different. The basic reason why we have these two kinds of errors is, of course, if you had an exact method, it doesn't matter where you start from. But heuristics require some assumption about the structure of the state. And so generally, heuristics always have some dependence on the initial information that you give it, which in this case is a mean field state. Okay, so this type of thinking has a close analog if you think about more of a condensed matter perspective. So in condensed matter, you can think about ground states as being, again, or bulk systems being classified into different phases. So there are many different electronic phases that a system can be in. And in each of these phases, there's typically some simple function that you can write down that describes a phase, right? So for example, these are the fixed points in the renormalization group theory of the phase. And the way in which heuristics work is that essentially you start with one of these fixed points that describes the phase. And the heuristic method allows you to explore nearby, right? For example, with perturbation theory, it's in some very real sense just nearby. But even these type of variational ansatz, because they have some limited degrees of freedom, they can only search nearby to their initial starting point. And generally, if you start from the wrong point, for example, the wrong phase, or very, very, very far from where you want to be, it's very hard to recover. Okay? So, and so the way in which you really perform classical heuristics in this treatment of systems is you have to and it's a very, very complicated system, is that you might have to try different starting points and then hope to glue together those solutions to get the full picture. And so that may immediately lead you to ask the question, how hard is it to get a good starting point? It doesn't sound like a very, if you want, guarantees and so on and so forth, this must make you feel very, uncomfortable. And there's sort of two possibilities for the answer to this question. I mean, it's not something for which I have a definite answer. But one possibility is that it's hard to get a good starting point because intrinsically, the starting point cannot be described classically. In other words, to obtain a reasonable qualitative description, the wave function doesn't have any, you can't write down any qualitatively correct wave function, in polynomial time on a classical computer. Right? So this is one possibility. There's no good classical starting point. But as it turns out, I am not aware of any case where this is true in natural chemical matter. There are many, many phases that people have identified, electronic phases, quantum phases, insulators, metals, superconductors, electronic crystals, various topological phases, and so on and so forth. It's a very, very long list. But in each of these cases, people have also identified very simple qualitative wave functions that describe these observed phases, right? So, you have all these why this is true, I don't know. This is like one of the mysteries of nature, but it appears to be the case. So there are all these famous theories, Fermi liquids, symmetry breaking, BCS, Laughlin, and so on and so forth. In each of these cases, these are just, when people identify the phase, they also find a very simple classical way to describe it. And so, it's my opinion that much or perhaps most of chemical matter has a very simple qualitative description. And in fact, if you focus on chemistry and not very exotic condensed matter physics, in fact, almost all of chemical matter is really close to a product phase, some type of broken symmetry state. Okay, but the second way in which this can be, it can be difficult to find a good starting point, is that you can say, well, okay, I know that the starting point is in one of these simple categories. It has a concise description classically, but I don't know which one it is, and I might need to search over many of them. Now, that type of problem really does occur. At least I've encountered many times in classical simulations. I already gave an example where you have these metallic clusters, and you have to think about the correct arrangement of moments. And this is, in that it is sort of essentially the same problem that people study in quantum magnetism if you think about spins and frustrated lattices. Now, it's similar to a satisfiability problem if you assume that the spins are classical. And so if you have a large system, if you want to check all the possibilities, this is a sort of NP-hard problem. And you have to search through all the possible classical spin states. And these problems do occur in real-life chemical systems. So the cost to resolve the reference error to solve this type of problem is then exponential in system size. But it's exponential in this classical way. Like in principle, you could be, not NP hard, but QMA hard, right? But I don't know anything that has that flavor. Okay, so at least in my practical experience, finding the good starting point for classical heuristics is more like an NP hard problem because you're searching through many just different classical type solutions for your starting point. Okay, so state preparation for classical problems is exponentially hard. That should be no surprise, but I think it's useful to think of the complexity of heuristics in that way. Go on.
Do you mean this is more like QCMA hard rather than QMA hard, as opposed to NP hard versus QMA hard?
I'm not quite sure what the definition of QCMA is. Is that QMA where the...
It's QMA where the
final state
reference state is a classical string.
I see. I think from the words that I've been saying, where I'm saying you always have this succinct classical description, but you don't know which one, that would mean that in the worst case it's QCMA. But I haven't encountered that kind of problem. So in other words, I've always found that at least in the problems that I'm aware of, they're more similar to just classical satisfiability rather than QCMA. Right? I mean, you can obviously construct problems where it should be QMA hard, right? So you can make a Hamiltonian for spins, just like in the original Kitaev construction, where you have like you can make some type of spin glass, but a non-classical Hamiltonian that's very frustrated, then find the ground state is in QMA. But I've just never come across a problem of that kind in real chemical matter. Okay. So now, let's see, what was I saying? So the problem of finding a good reference can be hard. In my experience, it's more like it's NP hard. Perhaps it should really be in QCMA, but I haven't found these cases. If it was in QCMA, it would mean we'd have no hope of ever doing it classically, right? But I just haven't found problems where you can make no progress by classically, searching over something. Okay, and then we have the question of the complexity of refining the result once you have a good starting point, right? So given the right starting point, what is the cost to refine the error? And there's really very little data on this question. As I mentioned, people just don't study this in classical quantum chemistry, but some of the first data was, I think, the stuff that we published in this paper here. And in this paper, we looked at sort of two classes of problems. One was main group molecules and biomolecules, where the mean field, Hartree-Fock mean field reference is just a good reference. It's very easy to find a good starting point, and you can just do coupled cluster theory from the starting point. And then the second was sort of Hubbard and Heisenberg models, where we use tensor networks. And so in these cases, we're basically we're interested in the cost to achieve a given precision. Okay, and the take-home message from these studies is that if you plot the error or the precision of the result versus the computational cost on the log-log plot, you see that in coupled cluster theory you have this kind of linear slope, and this is just telling you empirically that the scaling of the refinement is polynomial in 1 over the precision. Right? The cost to refining error is polynomial in inverse precision, and by some additional assumptions, you can actually though this is for a fixed system size, you can argue that this is polynomial in inverse precision even for a large problem, so long as the Hartree-Fock reference is a good starting point. And a similar plot for tensor networks, again, over just some limited range of heuristic parameters, in this case, a limited range of bond dimension, also shows this linear behavior. And so you also see this polynomial inverse precision behavior. Okay, so to summarize this part of the talk, classical heuristics are methods which you execute with polynomial runtimes almost by definition. But the complexity is not understood because the errors are not well characterized. And I think the field, well, when I say the field, I don't know how many people are doing this, but at least a small number of people are now beginning to try and correct this. And I believe that it's useful to categorize the error in two ways, right? There's a contribution from the starting point, which is the reference error, and then there's a refinement error. And I think for a lot of chemical problems, constructing a reference is easy because the problem is just close to some kind of product state. But there are, in fact, realistic problems where you do need to search over many of these classical solutions. And this involves some kind of exponential cost. And then limited numerical data suggests that the cost to refine once you have a good reference is polynomial in the inverse error. OK. And so I now come to the last part of the talk. I mean, if there are any questions of this part, yes, go on. Yeah. Yes, yes.
Is it possible that we only encounter classical ansatz because when we run out of classical ansatz, we just give up?
Yeah, this is similar to the previous question. Like, does everything look easy because we refuse to study hard problems? I mean, it's very hard to quantify that, but I can tell you that one is not actively avoiding things in the field, right? So we're not, I mean, I'm just saying, if you take out the list of problems that people study, they tend to have these features. And it's not like there's this entire other list of problems we know about that we refuse to study because we are worried that they might not be things you can tackle, right? As I mentioned, I think that chemistry, in the end of the day, has this simple structure related to, the reason why it has a simple structure is related to its definition as an experimental science and the conditions under which experiments are done. Because in chemistry, it's not done under, chemistry and material science traditionally is not done under conditions where you have control of the quantum state. It's done in a very dissipating environment, which I think promotes classical behavior, right? If chemistry were done with perfect control of the atoms and the electrons and no noise and so on and so forth, there would be other types of phenomena that would be relevant. But that's not really how the subject is defined experimentally.
Hi, I have a question. So referring to the part where you talk about the exponential initial state, is there any cost function that you can construct to decide which initial state is better than the other?
I mean, without knowing the answer, I don't think so, right?
Okay.
Yeah.
Yeah, thank you.
I mean, maybe you could look at the energy and one is lower than the other. But generally speaking, without the initial, any answer, you don't know.
One more question.
Yeah.
The plots that you shared just before, these slides before, these are for estimating ground state energies of systems, is that right?
Yes, yes.
Can you comment at all about this intuition that you're presenting for dynamical properties of systems?
By dynamics, do you mean the low-lying excitations, or do you mean like arbitrary non-equilibrium dynamics, or what?
I suppose whichever you think is more interesting.
Yeah, yeah, so the things I'm saying today, I mean, a few of them I've said before, and some of them I've never said before in particular. But when I have talked a little bit about these things, in particular in conjunction with this paper on exponential Coulomb advantage, there we were careful to frame things in terms of the ground state. And of course, the obvious question people would always ask is, well, what about the excited state? And my take there is like the way in which people think about the excitations in a physical problem is that, in chemical matter, which is not super exotic, there are always quasi-particles. So the excitations are very similar to the ground state. And so there isn't this completely different theory of the first excited state from the ground state. Of course, this is not universally true, and you can construct mathematical models where this is not true, but at least in physical problems, this is the case. The question of how to treat arbitrary non-equilibrium dynamics is a more complicated one. I mean, and I think that not everything is understood, but I would have said that there are two kinds of dynamics that you can do. The dynamics that's traditionally been relevant to chemical matter simulation is you perturb the system and it generates a local perturbation. And because it generates a local perturbation, and that local perturbation typically dissipates pretty quickly. So it doesn't generate some very, very complicated quantum states. But in modern discussions of the complexity of quantum dynamics, typically in condensed matter and quantum information, one's thinking about a different scenario, which is where you, for example, do a quantum quench of the problem. The entire Hamiltonian is changed in an extensive way, right? This is just not the setting which you usually conduct the experiment, but in principle, you can do that if you pump a lot of energy in. And there, of course, you can create lots and lots of chaotic kind of things. Classically, the complexity of computing things by heuristics is not well established in that case because people are only just beginning to work on those problems.
Thank you.
Yeah.
Also about the plots, the errors that you showed, are they the state preparation and refinement error, or they also include the stochastic errors?
The methods I showed have no stochastic error.
Okay.
So yeah,
Okay.
yeah. So they're really just showing the refinement error. Yeah.
So no Monte Carlo. No.
There's no Monte Carlo there. Yeah. Okay. All right. So the last part of my talk is really about quantum algorithms for quantum chemistry, which is probably more relevant to the conference, but it's the area I know least about. So let me just briefly discuss quantum algorithms in quantum chemistry. Okay. So to start off, we have to set the problem correctly. Most of the time, qubits are not fermionic, though it might become possible if you have fermionic cold atoms, for example. And so you have to translate the problem that I set up earlier, which is a fermionic Hamiltonian, into a qubit Hamiltonian. So you have to choose some encoding. And so there are many ways you can do this. The oldest way is to just use the representation, the sort of computational basis representation associated with second quantization, where you think about occupying or not occupying certain orbitals. And we can think of 0 and 1 as qubit labels. And then to do the fermionic, to encode the fermionic nature, you can introduce this Jordan-Wigner transformation, which converts the fermionic operators into these spin operators with these long strings, Jordan-Wigner strings. This is the simplest thing to do. The fermion sign, or the parity computation, is very non-local, and so it has some undesirable characteristics if you want more local encodings. And there are various ways to make more local encodings, some of which involve introducing extra qubits. There are also other representations. For example, you don't have to store all the zeros and ones. You can say, I'm just going to label the orbital which is occupied. So in this case, it would be like 1, 2, 3 and 4 are occupied, and 5, 6, 7, 8, 9, and 10 are occupied. So you can just store the labels. And this would be what you might call a first quantized representation of the state. You translate these labels back into binary, and then you can store them. You can choose as a qubit representation. But it doesn't really matter how you do it for what I'm going to say. So I don't think there are really major open questions in this encoding, but you have to choose some encoding to start the problem off. OK, so after you've chosen some encoding, then you have to find the ground state. And there are essentially two families of algorithms. The first are these variational algorithms. And I'm going to put in this category, some work that I worked on, which was this quantum imaginary time evolution, which isn't technically a variational algorithm, but has the same sort of classical feedback that you have in the variational algorithm. And these are sometimes termed NISQ algorithms. And then the other class of algorithms are, related to phase estimation, where you have to first prepare some states, and then you, for example, do phase estimation or something a little bit similar to that, where and then measure to project onto the ground state. These are usually toward fault-tolerant algorithms. Okay, so the two things that I'm going to cover very quickly are, just very roughly, how do these algorithms work, and in what sense should we think of them as providing or not providing advantage for quantum chemical problems. Okay, so I'll start with variational quantum algorithms, which are extremely simple-minded. You essentially take the energy, and then you just have some unitary circuit. The unitary circuit has some parameters, and you optimize the parameters by minimizing the energy. I mean, it's just a variational theorem. Now, when you measure the energy in this case, you measure it by measuring the individual Pauli operators of the Hamiltonian. And if your Hamiltonian, for example, is written in an atomic basis, it has n to the 4 Pauli operators. So you have to measure many things. OK, so VQE, I think in terms of the number of papers written on it, is extremely popular. And it's become super popular amongst quantum chemists, chemists doing quantum chemistry. Why it's so popular is I'm not exactly sure, but I think it has to do with 3 characteristics. I mean, one is that it's very easy to understand. So you don't have to know anything about quantum computing or quantum information to do VQE. And you can still be doing quantum computing. The second thing is, there's an infinite number of circuit architectures you can put in. So there's an infinite number of things you can do. Right? You can keep yourself occupied for a very long time. And then, of course, in principle, it's possible that there are unitaries here that provide compact descriptions of ground states for which there aren't equivalently, classically compact descriptions of ground states. Okay, so these are, I think, the 3 reasons. Okay, but there are many problems, and I think I'd be interested in this community what people think about work on variational quantum algorithms, because. Yeah, maybe people can tell me in private discussion. For chemists who have, tried to participate in the quantum gold rush, so to speak, they've just all turned to writing endless VQE papers because, as I say, it's very easy to do. But I have the sense that in the more mathematical quantum information community, this is not viewed particularly favorably. And I share that sort of opinion, if that's the opinion you hold. Because there's so many problems, right? So the one problem with VQE is, of course, you have to measure these things, and there's an enormous number of measurements, and all these Pauli operators have been measured to high precision, and you can write down these sort of tiny molecules like lithium hydride in some small basis, and just count the number of measurements, and it's just some number that seems absolutely enormous, 10 to the 9. And you can reduce this with some heuristics, but it's a very daunting prefactor just to get you started with a method. And that's for a diatomic molecule. And then in addition, you have to optimize the problem, optimize the circuit. And if you just choose, general unitary circuits, they're very hard to optimize. And there's even the idea that if you try and choose a circuit which doesn't have barren plateaus, perhaps that means that it's classically tractable. So actually, I don't know what people think of this work, but at least it was a paper with an interesting title. So from my perspective, this is one of those opinions I'll give out. I think VQE combines the worst of quantum, right, which is reading out, with the worst of stochastic classical algorithms, which is doing nonlinear optimization with noise. So it's a little bit mysterious why it's so popular in that for these 2 reasons. But I actually think there's actually a third problem with it, which is that it's not clear, although there was this, perhaps, all this would be okay if it was really true that there were that unitary circuits somehow offered this really concise description of problems that we wanted. We can get over the measurement problem. We can find ways to optimize. But it's not actually clear that unitary circuits are more expressive than other classical parameterizations for the states we want to study. Okay, so there's surprisingly limited evidence in physical problems for this. So the only evidence actually that I'm aware of is actually some that emerged in my own work, but I don't follow this field very carefully. So if there's other evidence, people, please do tell me about it. And in this work, what we try to do is we study lattice models where we're very sure about what the best classical representation is. Everyone would agree in the field that if you study 1D lattice models, if you choose a matrix product state, that is the thing to do. And what we tried to do in this work was we tried to compare the classical matrix product state description to representations of the ground state using a variational quantum circuit. So we're comparing this kind of matrix product state to some kind of quantum circuit, and we considered a variety of different quantum circuit architectures. And the questions we wanted to then understand is, are these circuits more expressive than the classical description? Right, so that would mean that you need fewer parameters to represent the state. And the second thing we want to understand is, are these circuits more computationally efficient? In other words, can you achieve the same accuracy with lower cost, because it could be that you use very few parameters, but it's very expensive to work with a circuit. Okay, so here is some of the data that we got, right? So this, I think, was in the 1D Hubbard Hamiltonian, I think. And this plot here shows the error scaling with a number of parameters for the classical matrix product state, here written as DMPS for various reasons. It's because CMPS means something else. It means continuous MPS. So here we wrote DMPS. And this blue data here, so this is the precision. This is the number of parameters. And then we also show the best quantum circuit parameterizations we could find. And you see that this blue curve here is above these red and orange curves. And this is saying that you need fewer, that the quantum descriptions are in fact a little bit more concise. Okay, so you need fewer parameters to reach the same precision. Okay, so if you choose the best quantum circuits out of the ones that we studied, they are a bit more expressive than classical MPS. Not by a huge amount, okay, but they're a little bit more expressive. But then when you look at the cost of working with them, if you turn the calculation of the NG here with this certain number of parameters into some precision scaling, the 1D classical MPS in this particular problem has a cost that scales like 1 to the square root of the inverse precision. Oh, okay, okay. Time is up. Okay, so the short story here is that I don't have too much more to say. Is that, I mean, you can see very, very weak evidence for small polynomial advantage for circuits in physical ground state representation. It's very, very small. But there are at least some examples where it's not zero. Okay, and that's at least the start. It's not clear whether that gets over all the problems with prefactors. Okay. Should I stop? Yeah. Fault tolerant algorithms. Okay. So I can talk for about, I'll try and talk in 5 more minutes, okay? 5 more minutes, okay? So in fault tolerant quantum algorithms, I'll just say, they have this general structure. You prepare the state, you measure the phase. They have some complexity like this, right? So there are many types of fault tolerant quantum algorithms, not just phase estimation, but they always have this type of complexity where you have this polynomial in the inverse precision, polynomial system size, and polynomial in some quantity that looks like the inverse of the fidelity in the beginning. Okay, so much like in the classical discussion, the polynomial piece here should be thought of as the cost of refinement, and this polynomial in the inverse overlap is the problem of preparing the state. It has the same structure as the classical case, and similar to classical heuristic state preparations where the complexity is hidden. And so there's really 2 ways in which you can compare quantum and classical simulation costs. One is about how hard it is to prepare good initial states for classical heuristics and for quantum heuristic or for quantum algorithms. And the other is how good are they at refining the errors, in this case by phase estimation. We know that in the worst case for quantum problems, state preparation is QMA hard. That's a well-known result. But for chemical problems, this I think is an entire red herring. I don't think the problems have this hardness to them. As I say, all known phases of matter have a compact classical description. So perhaps they should be in QCMA just from that statement. And in addition, find this classical description doesn't appear to be so hard. So perhaps it's not even QCMA. Okay. So I think it's useful just to assume that state preparation is not QMA hard. Okay. But also one should remember when thinking about these types of complexities that this feature that means that finding a good qualitative description is not very hard, and the qualitative description has a compact classical form is also at the heart of what makes classical heuristics work. So this is important in the thinking about advantage. Okay, so the end result, just to give you a very quick idea, is that we find that when we look at problems where it's hard to find a good classical state, in other words, you need to search over many different classical starting points to find a good state for your classical heuristics, it's also very hard to find a good starting point for your quantum algorithm. So if you do adiabatic state preparation, for example, if you start from different points, you have very different state preparation times in these types of hard problems. you can have this many orders of magnitude different state preparation times depending on your starting point. And so the fact that the classical state preparation problem has this sort of search problem associated with it that doesn't have some structure really just appears in the quantum algorithm, where this adiabatic state preparation time looks like the time you get when you apply the adiabatic algorithm to unstructured search, right, to a Grover search problem. Okay, so there isn't an obvious advantage for exponential advantage, for example, for the quantum algorithm in preparing the state, although there could be some kind of polynomial advantage that you kind of see in typical search problems. And the second question, and this is the last slide, is about energy refinement. So the energy refinement cost in phase estimation has this form, right, once you've got the state. And we can assume that it's the best thing you could write down. So you could imagine that it's linear in system size and it's Heisenberg limited. So it's just order inverse precision. And we saw that classical heuristics also have this type of scaling. But if you look in detail at the actual powers, the data I just showed you from the variational calculations in the 1D Hubbard model were order 1 on the relative precision. And if you turn that into the absolute precision, then this introduces a quadratic scaling in the system size. And so one sees that one has a quadratic speed up relative to, for example, the empirical scaling we see from matrix product states in this particular 1D Hubbard model application. And then in the 2D Hubbard model, the empirical scaling that we see has this much steeper power in the inverse precision. And that suggests that you have a large polynomial advantage for phase estimation in the refinement of the 2D Hubbard model as compared to 2D tensor networks. Okay, so that's it. So my opinionated summary. So while variational algorithms may have some role in the future, it's sort of, we need some more justification, I think, for why they should have some role in the future. And we need some evidence that they outperform classical methods. I think for fault-tolerant quantum algorithms, there is some evidence that they are useful, but it's useful to analyze the advantage in 2 settings, right? One is in terms of the state preparation advantage, and one is in terms of the refinement advantage. And I think there is now some empirical evidence, at least, of polynomial advantage in energy refinement. Okay, that's it. Thank you for your attention.